Научить они. Вот он входит в нас.
I checked with him and he said I was right. Here. This one. Yeah.
Oh, so this is this is just yeah. So this right here, yeah. Actually, this is been wrong already.
All right, we'll continue on. We'll pick it up right at number 4. That's where we left off. The idea that action potentials are non-decremental. So what that means is if I just draw the axon and its axon terminal,
And I was like, no.
if you elicit an action potential, a big spike, in the first part, and as it travels down, if you were to measure it at the very last segment, it wouldn't decay at all. It would have the same magnitude of strength. The AP spike does not decay, doesn't weaken at all. It keeps its full-on spike as the nerve impulse travels all the way down to the end. It's non-decremental. Okay, so this kind of gets to the next thing of continuous propagation. Continuous propagation of the AP is affected by the axon diameter in the leak of the charge out of the axon. Continuous propagation affected by a couple of variables. Axon diameter. Let's compare this axon to say a much smaller one. Axon diameter actually makes a difference. If you have a small axon diameter, if you look at the cross section, the cell membrane provides resistance. But the cytoplasm, we call it the axoplasm, that's in the middle here, there's more if you have more diameter, and there's less proportionally if you have less diameter. Axoplasm, less resistance. So, if you have a larger diameter, it's like the positive charges, it just kind of it's easier to travel down a larger diameter because there's more axoplasm, which provides less resistance. So the rule is, if you increase the axon diameter, you also increase the conduction velocity, and vice versa. All other things being equal. Now let's say you have a slight break in the membrane, leak positive charge. Leak affects it. If you increase the leakiness, you decrease conduction velocity. Let's say, for example, you have positive leaking out here. Well, at that part, it's basically harder to reach threshold because positive keeps leaking out. So with leak, it's harder to reach threshold. So that's why you see decreases in conduction velocity. You may see no nerve impulse. Okay, and the last thing is saltatory conduction. That's when you have the myelination. Okay, let's talk about saltatory. Well, let's stick with this here first. Okay, let me draw this here. Here's an axon terminal. And let's think of the axon in segments. I'm randomly going to segment the axon with these partitions. And what we had said was if you get an ax potential in the first segment, it doesn't go backwards, it only goes one way, right? So it'll jump to the next segment. It'll jump to the next segment. Call it this, whatever this length is from there to there, or there to there. Let's call that length x. Okay, because this determines the conduction velocity, this propagation. And so, my question is, what determines the length of x? And we answered the question I just asked. Axon diameter in leak. Let's say things are optimal. X is larger, X is smaller. So here's the concept. If X is, okay, let me just give you a second to think about that. Let's see. If X is longer, what's the effect on CV, conduction velocity? Faster or slower? If X is longer, it's faster. It's funny, I ask that question every year, and intuitively you think backwards. So let's think about this. X is longer, you speed it up. Why? If X is longer, then that means my segments are like longer, right? So I travel here to here. I go boom, 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 boom. I get down the whole thing faster if X is longer. Does that make sense? If X is shorter, I gotta go boop, 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 boop. Yeah, so that's the relationship between X and velocity. I can get across the room longer if I take faster if I take longer steps. 1, 2, 3, 4, 5. What if I take shorter steps? 1, 2, 3, 4, 5, 6, 7, 8, 9. It's like that, right? I go slower. Okay, so what can really make X longer? That's number 6, the saltatory propagation. Saltatory means to jump. So let's do an axon with myelination. All things being equal. Assume everything's exactly the same. And let's draw some myelination in there. Let's see how well. Remember, the myelination is by the glial cell of the Schwann cell, and myelination is fat. I'm not drawing it all the way around, but well, basically, because you insulate the axon with cell membrane, you make it impermeable to any ion flow. So even if there are voltage-gated channels there, they ain't doing nothing. They've been covered. They've been smothered by the myelination. But you may have voltage-gated sodium and potassium channels at the nodes of Grand VA. Where there is no myelination. So it is possible to stimulate right there, get a depolarization. The thing about it is, because you cannot have an action potential where there's myelination, you have to jump to the next node. That'll increase the length of X. So you just jump to here, get another one. Then you just jump, jump, jump till you get to the end. Okay? So that really increases the length of X and increases conduction velocity. Myelinated axons have increased CV because of that saltatory propagation. So think of a continuous propagation, no myelination, no jumping, it's just going steady and continuous. There's no ju, 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 ju. So a continuous propagation, associate that with no myelin. Myelin has the saltatory. I got a picture of that, I think. In this slide, I like it. I include it to show you a couple of things. That you measure an action potential at one location of an axon, and as the wave of depolarization passes by, when it passes by, you detect the depolarization. And this shows you that it can only go one way. It can't go backwards because immediately behind it, it's still depolarized. So that's one thing I wanted to show you. And it gives you a sense of how things depolarize and hyperpolarize, what it looks like as it passes by. This would be better if there were an animation. The other thing I wanted to show you were the myelinated and unmyelinated axons. See the top slide? I didn't do that one. This one assumes it's bare. There's not even any voltage-gated channels in it. You can get no propagation without the voltage-gated channels. You can stimulate the thing, but it'll die fast. But what we're saying is it doesn't die, because along the entire length, you have the voltage-gated channels. So each time you stimulate the next segment, you get your full spike. Full spike, full spike, full spike, because the segments are not that long. So we call this continuous propagation because there's no myelin. Here's the saltatory propagation where you get these big jumps from node to node. Here's just a nicer picture of it, the saltatory conduction. Now what's the end result of all this? To stimulate the next cell. It's great that you understand the nerve impulse, what we call the action potential. But when you arrive to the end, you stimulate the release of neurotransmitter. And you release it, you want to stimulate or inhibit the next cell. That's what we're going to talk about next. Stimulate, or sometimes you want to turn a cell off. Inhibit the next cell. Remember, nerves are in series. There are nerve pathways. You stimulate one cell in a chain to stimulate the next cell in the chain. That's what we have to talk about next. They call it information processing. It's actually not new information. At the simplest level, many dendrites receive neurotransmitter information, messages simultaneously. Some are excitatory, some are inhibitory. The net effect on the axon hillock determines if the action potential is produced. So here's a picture of a synapse. And you're trying to stimulate or inhibit the next cell. Here's the end of the previous cell where you had your action potential propagate all the way to the end. And things are either going to be excitatory or inhibitory. So call it IPSP or EPSP. So let me erase this. Okay, so let's go. EPSP. Excitatory postsynaptic potential. I almost never write that out. Just remember EPSP. The E is excitatory. Okay, this is anything, this is any graded potential that brings you closer to threshold. You're increasing the chance you'll stimulate the cell to turn on. Any graded potential that increases the chance you'll turn the cell on. So an IPSP is inhibitory. It's any graded potential that decreases the chance you'll turn the cell on. Just rewriting it, just changing increase to decrease. Any graded potential that decreases the chance you'll turn the cell on. So increases versus decreases. Turn the cell on, turn the cell off. And so let's show you a couple of pictures here. Okay, that is an EPSP because it's like you're closer to threshold. What do they use? Negative 55, yeah. It's a graded potential. Did you reach threshold? No. Did you get an action potential? No. But you got closer to threshold, so that increases the chance you could have got one. Okay. And so an IPSP will be the opposite, right? When you stimulate the cell, we should use the same one, I guess, the color. Stimulate. So you're at rest, and you stimulate the cell. It took you further away from threshold. So you're decreasing the chance you're going to get an action potential because if you go further away, well, you're certainly not going to reach threshold if you go further away from threshold. So that'll keep the cell off. And sometimes that's the goal. Now these things add up. Okay, maybe you want to turn the cell on, but maybe one excitatory one isn't enough. And they kind of add up. And the things you got to know are what's called temporal or spatial summation, shown here. So let's look at the picture. You're trying to turn the cell on. Here's the cell you're trying to turn on. Here's the cell that's stimulating or inhibiting it. What's exciting in here? All right, so if that's my, here's a good question. Is this cell presynaptic or postsynaptic? This cell, pre or post? It will be post because what we're considering is this axon. So that's the axon of the presynaptic, and that's post. You're trying to turn it on. Here's what you do. E1, this cell here, E1, stimulates there, stimulates there. Did you reach threshold? It looks like it goes, not quite, all the way return to rest. Stimulate again. Not quite, all the way return to rest. So that's a yes/no question. What if it were a test? What would you put? Did you reach threshold? No. You didn't get a big spike. So nothing. But what if you put the two stimuli close together, like stimulate, stimulate, instead of stimulate, wait, stimulate again. Put them closer together in time. Like kind of like zap it, instead of zap, zap. This is zap, zap, pretty quick. They add up. So it's like zap, oh, not enough, zap it again, and it reaches threshold, and you get the full spike. Okay. We call this temporal summation. It's one stimulus twice rapidly in succession. I'll just say two stimuli in rapid succession. Two stimuli in rapid succession. But it's only one input, right? One input, just fire that cell twice, zap, zap. This one is, I got two inputs, E1 and E2, and they're both firing once at different locations. That'll still summate too. Call that spatial summation. Let me go over here. I'm going to erase this now. Temporal summation. Spatial summation. So there you have two inputs. They fire once, but simultaneously, in different locations, in space, spatial summation. The inputs fire once, simultaneously, and that gets you the threshold. Reach threshold. And it's important to know that the two inputs, well, obviously they're in different locations. You can see from the picture. Fire from different locations in space. I'm going to say that because they call it spatial summation. I want you to make the association. Now, you could have inputs that are inhibitory. So this is what I1 looks like when it fires by itself. It's an IPSP. It's inhibitory. Maybe it made you go more negative. Okay, maybe that difference there. Maybe it made you go like -5 more. So when you pair it with an excitatory one, I guess they kind of cancel each other out. But in either situation, did you reach threshold? No. In this situation, you inhibited the cell further. In this cell, they just kind of cancel each other out. But in both cases, off and off. Nothing happened. So they are summating. They call this information processing. So if you put them all side by side, and you should be able to tell the difference between temporal versus spatial versus if you're adding it up with a stimulus that's actually inhibitory. Okay. All right, let me point to this. Yes, no, just shout it out. Did you reach threshold here? No. Did you reach threshold here? No. But here, yes, and yes. It's pretty obvious if you can recognize what an action potential looks like. So those are the last two slides. Temporal is one presynaptic neuron fired repeatedly at the same location to get threshold. But then you've got multiple presynaptic neurons. That's spatial summation. They each fire simultaneously, but in different locations. And some may be excitatory, some may be inhibitory. Okay. That concludes the material for this unit.